there. I'll begin. So, Heavenly Father, we thank you for this day. I thank you again for this class. Just pray that you be with us. Help us to glorify you what we do and just understand a little bit more about the chain rule today. Lord, in your name I pray, Jesus. Amen. All right. So, so yes, I will take this homework tomorrow, but there is a small late charge tomorrow. It is due today. So now if you still give it to me today, like a little bit later, I'll consider dropping the late charge. If you get it to me before I give it to the grader is the main thing, because I bundle the homework, I give it to the grader. I don't bundle the homework and then bundle it again and then bundle it again and give it to the grader. I give it to the grader once, So if you're late, then that disrupts the flow. All right, anyway, so there's your first top hat code for today. But why have one when we could have two? Because I forgot to do it yesterday, right? So I do have the attendance sheet to turn out, but I just... that was a sad top hat. 0325. There. Okay, proper top hat. All right, so if I can find my notes. So we're talking about the chain rule for functions of several variables. And so let me just get us started with an example here. What if we're given that w is equal to, say, x squared plus the sine of xy, all right? And maybe plus e to the z squared. And then we're also, something happened? Okay. And we're also given that x is equal to, say, u squared plus v squared. And y is equal to uv. And z is equal to u plus 2v plus 3. Well, just like that, I'm fine. So these are what's given. And then we're asked to calculate, like, let's calculate partial w, partial u, and what's partial w, partial v. How do we do these kind of chain rules? All right? So here's how it goes. The rule goes like this. We go partial w, partial u is equal to partial w, partial x, partial u, plus partial w, partial y, partial u, plus partial w, partial z, partial u. So we have to account for the change in each one of the quote-unquote intermediate variables. So here, these x, y, and z in this context are intermediate variables. That's the terminology that's sometimes used. So these are the intermediate variables. What's w is the so-called dependent variable. And the u and the v, these guys are the independent variables. That's the language here. So any chain rule problem, you kind of have to understand for yourself what's my dependent variable, do I have intermediate variables, and what are my independent variables. So we can calculate partial derivatives with respect to independent variables. If there's just one independent variable, it's not a partial derivative, it's a total derivative, all right? So, and then how do you actually do this? Well, it's pretty straightforward. And let me just go ahead and do it. So partial w, partial x is 2x plus, let's see, when I differentiate sine, I get what? I get y cosine xy from the chain rule, right? That times partial x, partial u. What is partial x, partial u? It is 2u, right? Then what's next here? Partial w, partial y is just this middle term, right? So we got a x cosine xy, all right? And then partial y, partial u, which is what? Partial y, partial u is what here? Guys, tell me? V, right? And then partial w, partial z is what? There's only one term up there with the z dependence, namely the last one. So how do I differentiate e to the z squared? I get myself a 2z e to the z squared by the chain rule, right? Like calculus 1 chain rule I'm talking about there, of course. And then I have to multiply by partial z, partial u, which is what? I guess I already did it, right? It's just 1. And let me just put a box around this and say this could be the answer. We could leave that as the answer. This would be an okay answer if I said you can use x, y, z for answer. In other words, that's an okay answer if I allowed you to use the intermediate variables to phrase your answer, right? But what is the truth here? Like, what does the chain rule actually say? I mean, this is just a shorthand for a more nefarious expression, right? We actually should plug in u squared plus v squared, uv, and u plus 2v into these expressions. That's actually what this means, all right? So this is subject the condition such that x is equal to u squared plus v squared, y is equal to, uv, and z is equal to u plus 2v, which I will write out. I'm going to regret doing this, but here it is. This is actually 2 times u squared plus v squared plus y was uv cosine of what you got there. Well, if I was smarter, what would I do here before I did this? What could we do before I did that if I wanted to make it explicit? It would be smart to group the terms with cosine together, right? So actually I have what? I have 4xu plus bracket y, my bad, 2yu, and then over here plus xv times the cosine of xy, right? I think I've got everything here now. No, I've still got the last term. So if I was going to plug in the explicit formulas, it's probably a good idea to actually do this before I do it, right? So that's 4u times u squared plus v squared plus bracket 2u times uv plus xv, so that's v times u squared plus v squared. All right, close bracket, cosine of xy, which is actually, xy would actually be u cubed v plus v cubed u, and then plus, oh man, well, I'm going to have to continue down here. My apologies for the double plus. Let's see here, 2 times u plus 2v e to the u plus 2v quantity squared. So if you can put yourself in my shoes and think about grading this problem, do you see why I would sometimes add the instructions it's okay to write the answers using x and y? Because I can actually see if you did it correctly, whereas once you guys plug these things in and make an algebra step or two, whoa, it's really hard to see who's right and wrong, Okay, so let's do partial w, partial v. I'll do it down here. What's partial w, partial v? We're going to do partial w, partial x, partial v, plus partial w, partial y, partial v, plus partial w, partial z, partial v. Right? And, well, you notice that the x, the y, and the z derivatives, they're still the same, aren't they? So like I can literally just rip off what I had before. You know, it's still 2x plus y cosine xy, right? Times something, plus x cosine xy times something, plus 2z e to the z squared times something, right? And you notice the only difference here is just that these guys are different, right? The chain rule, it's the same pattern, it's just now I've got the partial derivatives for the intermediate variables. And those are respectively 2v, partial y, partial v is u. That was a v before, just to be. Sorry, my u's and v's sometimes. I mean, I try to make the u a little bit curly. And then partial z, partial v is 2 instead of 1, right? And if you don't mind, I'm going to leave my answer in terms of intermediate variables for the sake of, you know, doing something more than writing the formula for this derivative all day, yeah? Does this make sense? Let's look at another example, yeah? Example 2, suppose partial w, partial x is x cubed, partial w, partial y is xy, and partial w, partial, well, let's just stop there. We don't have to have a z, all right? And you've got that partial x, partial u is equal to 1, partial x, partial v is equal to 2, partial y, partial u is equal to 3, and partial y, partial v is equal to 4 when let me think here. When u is equal to 5 and v is equal to 6. All right? Calculate partial w, partial u at 5, 6, and partial w, partial v at 5, 6. Now, my first question to you is, have I actually given you enough information to calculate these partial derivatives? Let's try it out, and you be the judge if I've given you enough information or not, right? So what would partial w, partial u look like here? It would be, so to be more explicit, guys, this is partial w, partial u at u comma v, all right? So the way that works is we've got partial w, partial x at u comma v, right? And to be more specific, it's really partial w, partial x of u comma v, comma y of u comma v. Oh my goodness, this is going to be horrible. Partial x, partial u of u comma v plus partial w, partial y, which is technically speaking a function of x of uv, comma y of uv, partial y, partial v, partial u rather, which is a function of uv. So we think of w as a function of x and y, but in the context of this chain rule, what we're really doing is to be more pedantic here, to start with, what I'm really calculating is partial u of w of x of u v, comma, oh man, I can't even fit this stupid thing in there. Rats. See, if I had that wall space to use, we would have made it. But try it again here. So this is actually equal to partial u of w of x of uv, comma, y of uv. So like, specifically speaking, w is a function of x and y, all right? I didn't tell you what w was, did I? No, I just told you that the derivatives of w with respect to x and y were what they were, right? Okay, so let's see if we can put the pieces together here. What is partial w, partial u of 5, 6 equal to? Well, supposedly, it's what? It's x cubed times what? Partial w, partial x, partial u, right? At the point, what was it? 5, 6? So what is partial x, partial u at 5, 6? I told you it was 1, right? And then partial w, partial y is xy. And then the partial derivative of y with respect to u was given to be 3, right? So you see, I haven't given you enough information, right? Because you can't tell from what I've given you what is x and what is y when u and v are respectively 5 and 6, right? So let me tell you those. And here's where I'm going to get into trouble, because I can't just make up anything, technically speaking, right? Why are the values for, well, how about this? Let me make sure my problem makes sense. So can you tell me what's a reasonable w? What could w have been, hypothetically? There's actually an infinite family of choices. Or is that even possible? Oh! Check it out, yeah. Check it out, guys. So, is this even possible? What are we stuck with? For as long as I say the function's smooth. All right, let's suppose that it's twice continuously differentiable. So we have Clairaut's theorem, right? Is that even possible? What's the deal? We know, remember, that partial squared w, partial y, partial x, right, is equal to partial squared w, partial x, partial y, right? But that for my formula says what? 0 is equal to apparently y. That's a problem, right? So if I try to find the w that differentiates both to that formula and that formula, I can't do it. Unlike the problem you just did on your homework, right, where you were able to find the potential function that differentiates to give you back the vector field at the end. So this, you can't just undo partial derivatives when they're linked, just willy-nilly. Like there's consistency relations that have to happen between the mixed partials that are very demanding. So I can't just make this up, right? So in short, this problem, I think this helps illustrate the chain rule, but it also illustrates some of the dangers in just writing things down. Now, how can we fix this problem? Well, if I just told you values for partial w, partial x, and xy, that would work, right? But I think we can stop this example here. It served its purpose, all right? So we say we reject example. Impossible. Right? If I give you a test question, right, and you find convincing proof that my problem is impossible, you should say this is impossible, and then you should come and tell me immediately. And then I will either tell you, yes, that was on purpose, congratulations, you found the trap, or, hey, everybody. It is impossible, but ignore that. Pretend it was. See, we could pretend this was possible, and then like the next thing would be this, right? Partial, x, partial x, partial v would have been 6, and partial y, partial v would have been 4, All right, so example 3. suppose you have w, which is equal to some function of x, y, z, all right? And you have x, y, and z functions of u and v, all right? Instead of u, we've been using u and v too much. Let's use s and t for a change, all right? And you have that wx at 3, 4 is equal to 1. wy at 3, 4 is equal to 7. wz at 3, 4 is equal to 8. And we have that x of 0, 1 is equal to 3. And, oh man, my bad. Do you see how I can fix this? Rats. I can't keep track of my, I said w is a function of 3 variables, right? So I need to add a thing here. Let's say 3, 4. You guys pick the number. What do you guys want my third number to be?
5.
5. Okay, I like that. 3, 4, 5. So x of 0, 1 is 3. Y of 0, 1 is 4. Z of 0, 1 is 5. All right? And then let's see here. What else do I need to tell us? And let's see here. X sub u of 0, 1 is, I need some new numbers, 13. X sub v of 0, 1, 14. Y sub u of 0, 1, I'm starting to regret this example, 15. Y sub v of 0, 1, 16. Z sub u 0, 1, 17. Z sub v of 0, 1, 18. Ah! S equals to, son of a gun, st, st, st. Did you notice that at the start of when I was writing that or at the end? You monster. All right, so you know what you did. All right, so now that we have all of this horrible data, we can calculate what is partial w, partial u, when u is equal to 0 and v is equal to 1. So it is partial w, partial x at 0, 1, partial x, partial u at 0, 1, plus partial w, partial y at 0, 1, partial y, partial, I'm doing it again, s, 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 there, s, not u, trying to use s, plus w, partial z, at the point we're given, partial z, partial s. All right. And again, technically these are at 0, 1. All right, so I've given us all these values, right? So what is partial w, partial x at 0, 1? And by that, of course, I mean 3, 4, 5, because that's where x of 0, 1 is, all right? So, so that's actually wx of 3, 4, 5, given the context, and then x sub s of 0, 1 plus wy of 3, 4, 5, y sub s of 0, 1 plus wz of 3, 4, 5, z sub s of 0, 1. And then we just put in the data we were given, which was what? So we got 1, x sub s was 13, w sub y was 7, y sub s was 15, W sub z was 8, and z sub s was 17. All right? Now, if you'll forgive me for not writing absolutely everything out, let me just write down the other partial derivative here. What is partial w partial t at the point 0, 1 equal to? Well, we do the same x, y, z derivatives. So the intermediate variable derivatives are just the same as they were, same as it ever was. But the partial derivatives of the intermediate variables with respect to the independent variable t are different, right? They are, instead of 13, 15, 17, we've got 14, 16, 18. Right? Are any of you guys in Math 221? You're doing matrix multiplication right now? Some of you? Yeah. Can you see any matrix multiplication going on here? Let me make some comments here. So we've got what's the composition we're looking at? Like W is equal to F of what? X of UV, Y of, I did it again, good grief, ST, Y of ST, Z of ST. So let me just try to keep track of things. Like the mapping is like this. We're taking ST, then we're mapping it to XYZ, right? And then we're mapping that back to W. Right. So essentially it's like a mapping from R2 to R3 back to R again, right? So if it's a linear, if we're talking about a linear map in like Math 221, which you might not have done yet, or ever actually, but this kind of thing, we actually use what's called a 3x2 matrix to get from here to here. And this is an R1, so here we would use a 1x3 matrix, if I remember right. So let's see here. If I make the 3x2 matrix, basically I'm going to make the let's see here. So I think if I put 13, 15, 17 here, and if I put 14, 16, 18 there, and I take that and I multiply by, see that's 3x2. No, I think I need, Rats. Just not seeing the pattern at the moment.
That seems like the size we've been using for linear transformation.
Yeah, I'm just trying to just a second here. What I wanted to see was like partial W, partial S, and I think partial W. I may be remembering my formalism wrong, guys, here. we'll have to get out the notes in a second, but this is like, so I think I need to put this matrix sideways. That's not right. I'm sorry, guys. I'm all turned around here. I'm going to bail on this for the moment. I can't. Let me get out the notes and I'll show you. Anyway, sorry about that. So the itch I was starting to try to scratch and unsuccessfully so far was, where are the chain rules coming from, right? Because that's an obvious question to ask. I mean, I've just written them down as if they're received from on high, right? How am I inventing these chain rules? Where are they coming from, right? There's actually a natural explanation if we look at the composition of the functions and then look at something called the quote-unquote general derivative. But I shouldn't try to write that out. I should project it to show you guys how it works because I have the formulas there more correctly written. And I'm getting confused about which is the domain and which is the range. It's that kind of confusion right now, so I'm not going to see past it. But I'm going to suspend that thought and come back to it at the end of lecture because we need to do more examples before I get derailed into explaining where the chain rules are coming from, right? So another example we should look at. In fact, one of the most important uses, so the larger point of the last example is just that you can't always just use formulas, right? Sometimes we give you numbers, you have to follow the chain rule, right? If I had see the thing is, if I have a formula for everything involved, you can always just, like this problem, example 1, right? If you go back to example 1, there's another way to do this if you don't know the chain rule, right? What is it? What's the other way to do example 1 if you don't know the chain rule? You just plug in the formulas for u and v, right? You just plug the stupid formulas in and differentiate. You get the same formulas, right? But that's not always possible because sometimes an evil Calculus 3 instructor, instead of giving you formulas, gives you a bunch of annoying data that you have to work with because unless you understand the chain rule, you can't solve that problem, right? And a more nefarious instructor would give you a problem like this where the point of the problem is to understand that it's not possible. So, yeah. But there is a more interesting kind of chain rule, I think, which is just coordinate change. If you have a formula which is defined for one system of coordinates, can you change it to another? In other words, so thinking about two variables, right? Thinking about two variables, example 4, we have, partial f, partial x, right? And partial f, partial y for functions of x and y, right? How to relate to a partial derivative of that same function with respect to the polar coordinate r or the polar coordinate theta, right? So here's how that goes. Partial f, partial r, we write as, so let's think of it this way. Partial r of f of what? We're thinking of f actually where we have x as a function of r and theta, right? And we have y as a function of r and theta. Okay? How would we do that? Well, the chain rule says we do partial f, partial x times partial x, partial r, plus partial f, partial y, partial r. But what is partial x, partial r? I mean, you guys know these, right? What is x? What is x as a function of r and theta? And what's y as a function of r and theta here? What are these? Remember, this is r cosine theta, and this is literally r sine theta for polar coordinates, right? So what is partial x, partial r? You've got cosine theta, partial f, partial r, partial x rather, and then apparently plus sine theta, partial f partial y. Nope, the r got differentiated. That's the point. Now, on the other hand, partial f, but we could go the other way, right? We could go, what's partial f partial x? Well, partial f partial x, we could also write as like partial f partial r partial x, plus partial f partial theta partial x. We could do the chain rule this way as well, changing from x variables to an r and theta variable. Now the derivatives, how do you find partial r partial x and partial theta partial x? Well, that's more, a little bit trickier, right? We do know this. We do know that r is equal to the square root of x squared plus y squared, right? And we know that theta, and for the simplicity of this discussion, let's assume that x is greater than 0. All right, so theta is inverse tangent of y over x. It turns out the differential identity that we get from differentiating theta with respect to x is likewise true in the other quadrants with the proper extension of the concept of angle, but that's a longer story. Anyway, so partial r partial x is what? I think we worked this out last time, right? So you got partial f partial r. Partial r partial x would be actually x over r, right? And then we've got plus partial f partial theta. Let's see here, what is partial theta partial x equal to? 1 over 1 plus y squared over x squared times minus y over x squared. That is minus y over x squared plus y squared, which is also known as, well, we can write it like that, right? So minus y over r squared. We can clean this up a bit, right? If you want to write that in terms of polar coordinates, you could also write that in terms of like, well, this is the question, is like, what kind of formula do you want here? We could either express it in terms of Cartesian variables, or we could express it in terms of like polar variables. I'm going to go the polar route just to do something here. So this would be, what do we got there? Partial f, partial r. What's x over r? X over r is cosine theta. And then we've got, what's y over r squared? That's minus 1 over, well, minus, good grief, partial f partial theta times like minus, come on, times sine theta over r. So what do you think is going to happen if I was to calculate partial f partial y in the same way I just did it, right? And I was to plug it, and I plug both of those expressions back up into here. What do you think would end up happening? I'll tell you what would happen. If I plug this and the analog of that for partial f partial y up into the blue expression here, everything's going to cancel out. I'll get like sine squared plus cosine squared, and I'll eventually obtain the equation partial f partial r equals partial f partial r. So that would not be terribly interesting, right? But I wanted to show you, you can go both ways here. Let me start on something a little bit more harder. A little more harder, is that a word? How about this? So Laplace's equation is what? It is like fxx plus fyy equals to 0. This is what it looks like in Cartesian coordinates, right? Natural question to ask is, what does that equation look like in polar coordinates? How would you change this? So I'm not going to do the whole thing. I'm just going to look at like half of it and like leave the rest of it to you, okay? But how would we actually calculate fxx in terms of polar derivatives? Well, that's partial partial x, right? Partial partial x of f, right? And so if you look at what I have here, there's another way to write this, which would be cosine theta partial r, minus 1 over r, well, minus sine theta over r, sine theta over r partial theta. See, that is the differential operator here, which acts on f. In other words, I can think of this chain rule as showing me something. It's showing me that the partial differentiation with respect to x, you can trade it in terms of polar partial derivatives. That's what it is. So if I want to switch the second partial derivative of f with respect to x to polar coordinates, I trade these x partials for those polar partials. In particular, you've got like cosine theta partial r minus sine theta over r partial theta, right? That acts on what? Well, that acts on cosine theta partial f partial r minus sine theta over r partial f partial theta, where I've just gone back to here, okay? Then what? Oh, see, that's where the interesting stuff happens, you see, because I've got like cosine theta partial r of what? Of cosine theta partial f partial r, right? And then, let's see here, plus cosine theta partial r of minus sine theta over r partial f partial theta. And then minus sine theta over r partial theta of cosine theta. I usually make this homework. Why am I doing this? Partial f partial r. And there's, let's see, so this is 2 things times 2 things. There's 4 things to consider. The fourth one is what? Sine squared. So this, oh, it's not, I can't just do that. It is plus sine theta over r times partial theta of sine theta over r partial f partial theta. And then the thing is, you have to think about product rules here, some of these. Now, some things pull out, right? Theta is independent from r, so we pull that out, right? So like the first term we get here is a cosine squared theta partial squared f partial r squared, right? That's easy enough. What's next? Well, this here, I have to do a chain rule. So that's actually the differentiation 1 over r is 1 over r squared. So I actually get plus sine theta cosine theta over r squared partial f partial theta minus cosine theta sine theta over r times partial squared f partial r partial theta. All right. And then what's next? That's, so far I've just covered the first 2 terms. Now this here, again, I've got a product rule. I have to deal with it. So that gets me a plus sine squared theta over r partial f partial r. All right. And then minus sine theta over r, well, sine theta cosine theta over r partial squared f partial theta partial r. And then over here, we've got ourselves a sine theta cosine theta over r squared partial f partial theta plus sine squared theta over r squared partial squared f partial theta squared. All right. You can see why I made this homework, right? I hope I'm not doing your homework right now, but I might be. at least part of it. So if this is fxx, right? What do you think happens with fyy? So like, what does the y derivative look like? What's partial f partial y? It would be partial f partial r partial y, right? Plus partial f partial theta partial y. And so what is partial r partial y? Well, partial r partial y is actually y over r. Y over r is nothing more than sine theta. So we get a sine theta partial f partial r. And then the partial theta partial y actually ends up being x, instead of minus y over x squared plus y squared, it ends up being x over x squared plus y squared, which ends up giving you, instead of minus sine theta over r, you get a plus sine theta over r. Plus cosine theta over r, rather, when you work this out, all right? So this shows you what partial, what fy is. And so if you did that again, a calculation similar to this, what's going to happen? If you start thinking about it, you can see you're going to get like this kind of term again, right? And you're going to get this kind of term again, but what's the difference when you do the yy derivative? Yeah, sines and cosines flip to the vice versa, right? Which means you'll end up with a cosine squared plus sine squared for both of those terms. And then, does anything in the middle already cancel? I wonder if I have, well, if I did this right, they don't cancel, do they? But these are the same thing twice, right? But when you do the other derivative, you get those terms again, so those mixed terms end up canceling. But I do think, if I recall correctly, we keep, well, let me not speculate, but there's a lot of things that cancel, but a few things, I can tell you this much. Part of fxx plus fyy is equal to, so you have frr plus, I don't remember, and then plus 1 over r squared f theta theta. So like the Laplace equation in polar coordinates, it looks different. It's not the same equation. The Laplace equation in polar coordinates is not merely frr plus f theta theta equals to 0. That's not the Laplace equation in polar coordinates. The Laplace equation in polar coordinates picks up an interesting radial dependence, and there's also a term which is linear in the derivatives, which I might have in my notes, but let me look for a second here. Are you guys good? Can I get out the projector now? I should show you a few more things here. Huh. So, there are various strategies for remembering chain rules. I just look for the pattern, and then I just try to replicate the pattern. Some people like these like tree diagrams. Like I put the dependent variable up top, I put the intermediate variable on the bottom, in the middle rather, and then I put the independent variable on the bottom. And then you just have to add, for every possible path there is to the bottom, like these kind of paths, you add a term. So some people find this a useful mnemonic to remember the chain rule. I don't really use it, honestly. But I mentioned it there for you. Now, let's see here. So we talked about the chain rule for paths composed with paths substituted into functions like of xy or xyz last time, right? And I talked to you some about the geometry of that. Let's see here. So today we've been mostly talking about, I'll get to it eventually here. things like this, right? Like, suppose you have a function of two variables, x and y, and then you've got x and y are also functions of, you know, r and s in this case. Then we can calculate partial z, partial r, partial z, partial s, like that. And if you were so inclined to calculate the second partial, you can do that. But then you have to differentiate your rule for the first partial, and you end up with product rules, and yeah. So there is what partial z, partial r squared looks like in terms of partial z, partial x, second derivatives in x, mixed derivatives in x and y, and the second derivative in y squared. So this is a nice, easier version of what I was just doing with the polar coordinates, right? Which is to change, I'm changing partial derivative in a new variable, and I'm converting it back to the old variable by just using the chain rule, differentiating the chain rule essentially. So let's see here. So right here is the example we were just doing essentially. But I think this is maybe from the other direction, right? So I was just explaining to you how we can convert partial x into a linear combination, if you will, of partial r and partial theta. This is the other way. Like I can write partial r as this combination of the x and y derivatives if I just look at the chain rules right up there. So you could go either way. See, here's the one we were just deriving these, right? And here's what I was just working out. Although in the notes there's a significant jump, right? So I just showed you like half of this. I was just focusing on this, right? And I didn't do the other half really. But after the dust settles, you can kind of already see these last two terms from what we talked about, right? No, my big phi is just what I was using f rather than big phi. Don't be distracted by the letter, but it turns out that there's a 1 over r partial phi partial r. That's actually the term in the middle that I couldn't remember exactly how it goes. I think if you stared at the terms a little bit longer, you probably see it. But oh, here's a hideous example like we did, example 3. Let's see here. Well, we'll talk more about these kind of examples probably tomorrow, maybe. I'm just trying to make sure I haven't forgotten anything, you guys. So here's the matrix calculation I was talking about. So if I'm thinking about like a function, I'm setting w equal to a function of x, y, and z composed with, and where x, y, and z are functions of, that's actually the pattern I had over here, right? My w is a function of x, y, z, right? Wow, I even made the letters match up. It's almost like it was on purpose. So s and t are the variables for the, the intermediate variables, right? Then I point out that if you take this row vector, partial f, partial x, partial y, times this is a 3 by 2 matrix. So here's the s derivatives of x, y, z, the t derivatives of x, y, z right there. You multiply these two, that actually will produce like these numbers that we had here. Because for my example, let's see here, the x, y, z would have been, I can't see anymore, 178. And the other one would have been 13, 15, 17, and then 14, 16, 18. So this gives you
let's see here. Well, I don't want to calculate those numbers. My point is that's the same pattern that we had over here. It's not an accident. Those are exactly the chain rules for partial W, partial S, and partial W, partial. Well, that's a typo right there. Did you see that? So this times that gives me this. That times that gives me, it should be partial W, partial T right here. All right, so let me, oh, here's the tree diagram for those. Like, I don't know, like whatever. So let me go back here a bit. Let me just talk about the general concept of a derivative for a bit. So I've talked to you about partial differentiation. I've tried to tell you about chain rules. My apologies. I really think I lecture better not at 8:15, and this lecture is a particularly good example of that. And so I'm annoyed. I have much more to say here than I have this morning. But anyway, you can see that if you read the notes, right? Please read the notes on the chain rule. I have so much more to say there. But the general derivative is something we should talk about. So this right here, I definitely will not test on. All right, this is really advanced calculus. To fully understand this section, you need to understand like matrix math, all right? But that said, there is a conceptual thing I want you all to understand that I would test on, and that is the concept of a linearization. All right, so what is a linearization? Well, if you've got a function from, say, so many variables to so many variables, a natural question asked is when can you like replace that that nonlinear function with its best like linear approximation? And in short, that's what the general derivative does. Is it gives you a way of replacing a nonlinear thing with a linear thing, and that's what the derivative is. So here is the careful definition of it. If I've got a function from Rn to Rm, I can define what's called the Fouché derivative of such a function according to the vanishing of this particular quotient here. That's called the Fouché quotient. And so if you just, don't get lost in the details, what's going on here is we're taking the difference of the function at a little bit further and the function at a point. So this is the change in the function, right? That's being well approximated by this term, which is called the linearization of the function. That is exactly what's called the differential. And that differential, the matrix of the differential is a linear transformation for those of you who know, but you probably don't yet. That's okay. But any linear transformation has a matrix called the standard matrix. The standard matrix of the differential is this f prime of a. That is actually a matrix full of partial derivatives. The partial derivatives form the matrix here. And the matrix of that derivative, well, let me tell you what this does. So in short, the idea is that the linearization of a function is the value of the function at the point plus the matrix that of the differential times h. This is the linearization. Now, this single idea covers many things that you've already done. First of all, it covers the tangent line in Calculus 1. So in the context of a function from R to R, the linearization is literally f of a plus f prime of a times h. This is the tangent line approximation. All right? A little bit earlier in this course, we talked about the tangent line to a space curve, right? That would be r of a plus r prime of a times h. That is, again, an example of the linearization, right? We will soon talk about z. Well, this is a little more general than that, but if I had a function from Rn to R, I can linearize it by the point, the value of the function at the point, and then I take the gradient of the function and I multiply it by h. This is a formula for the linearization. Coordinate